So before Simplex, and I will first describe some challenges faced by developers, and then we'll go to a project that we wrote before Simplex, and then we wrote it with Simplex, so we can see what kind of the architectural differences are, and kind of decisions that that make this project run. So before Simplex, devs had to manage simplicity contracts themselves. What it means is usually they would call like a compiler either directly through a CLI or use a Rust crate, basically a like compiler Rust crate that would compile the programs for them. There you would basically manually need to construct a transaction environment, provide all the necessary information in terms of UTXOs of this transaction, so that we can execute the program and understand what witness needs to be provided to spend this program in a real environment. So this second bullet point is kind of nasty to assemble manually, because you need to provide all the necessary UTXOs for the certain smart contracts that you want to spend. You need to fetch those UTXOs from somewhere. You need to filter them. You need to construct a lot of stuff that is actually shouldn't be done by developers themselves. Then, because every simplicity smart contract, it has like two ways of interacting with it. The first one is providing arguments at compile time, and the second one is witness at runtime. So when you want to spend it, you provide witness. And those two structs, arguments and witness, need to be encoded. You need to think what the names are of arguments and witness. You need to manually and correctly provide all the types, and those types can become super difficult to even to read, not to encode. Simplex simplifies this step a bit, but unfortunately right now it doesn't automate everything. So we have kind of some abstraction leaks here, which we'll try to solve. Probably will need some changes in the compiler itself, but yeah, it is what it is right now. Then there was no way to properly test the flow of the DApp. So of course you can, and you could write a simplicity program. You can write a Rust kind of wrapper around it, and you can write unit tests to see, for example, that, okay, the pruning on this program works, or that you correctly encoded witness and the pruning didn't crash or something like that. But of course, you want to deploy this contract to a real network, want to spend real UTXOs with some real signers. For example, your DApp flow maybe not a simple smart contract. It may be a set of smart contracts that interact with each other. Of course, you need to test it. And before Simplex, one thing you could do is to host a regtest yourself. So kind of spin up the regtest on your laptop and then connect through some provider and just manually write this flow down. Or you can just interact with a testnet and test everything there, but then you need test tokens. Testnet may be slow. If your DApp flow is kind of 5 steps long, then it will take like 5 minutes for the test to complete. You may be rate limited and all that kind of stuff, which is not really cool for development. Also, from a bit more technical standpoint, there were no kind of available, just clean Rust crates that would interact with Explorer API and Elements RPC. You had to dig somewhere and find those files, which are not the way. Or manually implemented, which a lot of folks did. Also, there was no simplicity-aware signer that could understand what's going on in the transaction, sign it properly, ruin everything, provide a correct fee estimation, and all that kind of stuff. So what people did, either they wrote their own signers that they just worked for their purpose, or just use signer that didn't know what to do with simplicity programs. And because of that, the developers just wrote a lot of boilerplate code. I just estimated that kind of 80% of that of the DApp is a boilerplate code, either the encoding of witness arguments or transaction building, which exposes a lot of internals. So yeah, basically the goal is to decrease this number to a much lower one. So let's then quickly jump into the code. So this is the project that we wrote without Simplex. So it's a basic lending protocol. It's a peer-to-peer protocol where borrowers can create offers and lenders could accept them. They could, borrowers could set up like the required collateral amount, lending duration, all that kind of stuff. So the actual tokenomics of the protocol are not super important right now.
Artem, I just want to mention that next week, a week from today, Sergey is planning to demonstrate the lending protocol as a use case, as an application. So for those who are interested in the details of the lending protocol as a financial application, we will have a demo 1 week from today about that part, as opposed to the mechanics of how we use it as a smart contract.
Yeah, so I won't cover today the economic internals, more the actual code, the technical side of the operation of this protocol. So the repository structure is the following. So it's a basic Rust. Actually it's a monorepo, but we need this crates contracts thing. So the contracts is where our simplicity contracts live. We also have the CLI and the indexer. Indexer is not important right now. This one is used to scan the blockchain and to correctly present UTXOs to the correct users on the front end. And CLI is the actual kind of front end, because so this is a huge difference between UTXO-based chain, for example, Liquid and Ethereum, that we need to compile smart contracts on the front end, because UTXO is just kind of a pointer, an encoded pointer to the real contract, and we need to provide the spending information somehow to the UTXO to be able to spend it. And the only way to do it is to just compile the smart contract from source and prune it to get the witness. So that's why we need to run everything in browser. And basically this CLI is this browser bridge right now. But in terms of smart contracts, so let's just take a look at some covenants here. So we have 4 of them. The lending flow starts with a prelog, which the borrower creates. This covenant is like a promise that borrower wants to take some funds, like to take credit. Then we have a lending covenant, which when the what's it called, the lender, when the lender accepts the prelog, the promise, then the lending covenant gets created, and lending can be, for example, liquidated. You can repay the loan and just do the basic lending stuff. Then there are two utility covenants, asset oath and script oath. They are needed because everything needs to be compile time. And these are like basically some hacks to make it work. So yeah, let's take a look at the lending. I'll just quickly show the simplicity file here. So it's not super important what it does right now, but I just want to show that it's a pretty complex logic, despite a basic, business logic implementation. So this is just one of the complexities that simplicity developers need to work with, is the actual complexity of the simplicity language itself. So as you can see, there are a bunch of like not so pretty calls to yeah, it's not actually a jet, it's a function, but there are a lot of calls to jets. And what this smart contract does is it basically restricts like the transaction formation to a specific like number of inputs, outputs, with specific assets, with specific script hashes and all that kind of stuff. So that only the like real business logic can be executed. And yeah, it's really hard to test it. And simplicity is not a Turing-complete language. We can have, for example, convenient tests written in simplicity. So we need to write tests externally. But yeah, as we can see, we have a witness here that we read. And also, there are some parameters that we also read. So witness and parameters need to be constructed. And here are two actually boilerplate implementations of this construction. So yeah, here we are building our arguments. These are the ones that are required to be passed at the compile time to compile the covenant. And here is the witness construction, which is simple in this case. So ideally is to get rid of those two entirely and make, some code generation that would build everything for you. So this is just the compilation thing. Then we have an SDK that actually builds expanding conditions of those covenants. As you can see, it accepts like super a lot of parameters, like some UTXOs that this covenant needs to be spent. And everything is explicit in our case. And yeah, just a lot of checks, a lot of getting addresses, compiling addresses, and constructing, yeah, just constructing the transaction. Basically, this function takes all the parameters and tries to construct a transaction for us that would create a lending covenant for us. And just by looking at it, we can see that like a lot of code is written, which is not exactly business logic, but rather boilerplate code. It also handles the fee that, yeah, it must be handled, but it shouldn't be handled by any, user code. It needs to be automatic. For example, the loan liquidation looks like that. So also a lot of parameters, a lot of just calls to fetch stuff, to parse stuff, and everything is like super explicit, which is not, nice to write. Yeah, then this code actually gets used in the CLI. So, for example, we have a CLI command lending. And in our case, it is also extremely explicit. So to repay a lending loan, we need to provide all those parameters because we didn't have a convenient way of, fetching them through a nice interface. And basically everything needed to be done manually. We also provide a Boolean flag to broadcast a transaction or not, which is just funny to pass in CLI right here. And yeah, just let me find the correct function and liquidate. Okay, yeah, repay. So here is the actual code that is run in the browser. So we are fetching UTXOs explicitly through some custom functions. Here is this function I showed previously that builds a transaction for us. A lot of Rust code and Rust internals is exposed here, which is awful to look at. We also need to construct this environment. So here are the UTXOs that belong to this environment. Yeah, we need to get the lending params here, and then we need to finalize a transaction. And then we need to calculate everything manually to construct it properly to provide correct, script hashes and all that kind of stuff. Then we are also final. So basically, finalization is the calculation of witness and inserting this witness into this transaction. So we are passing the transaction, calculating witness for some specific script, and then inserting it back. So we need to do it for every script present here. We need to calculate signatures, and yeah, it's pretty explicit, pretty verbose, and it actually doesn't need to be this way. So yeah, we wrote a bunch of code here, which actually works. Sergey will show everything next week, the user side of things. But then when kind of Simplex got to the alpha stage, to the testable alpha stage, we rewrote everything to it. So the repository structure after rewriting to Simplex remains kind of the same. So we have the CLI, we have contracts, we have indexer. Indexer actually didn't change at all because that flow didn't change at all. But the contracts directory changed a lot. So now we have a config file, simplex.toml, but yeah, it is just a commented out config because Simplex just needs this file to be present in the project to understand that it's a Simplex project, but the config can be empty. Then we have the simplicity covenants here. They're organized in one folder, so we can easily check everything. Yeah, and then we have a source for basically construction of transactions. So taking a look at the lending, the same lending covenant that I showed before. So what it does right now, it is basically like a wrapper around what Simplex generates for us. So I will show this generation process after that. I just want to showcase how the project structure changed. So here is our lending kind of object. We can construct it, and inside we have a bunch of functions to work properly with the program. So as you can see, it's a pretty simple and straightforward file. And then the same repayment transaction looks like that. So we want to construct a transaction. So previously it was a low-level partially signed transaction provided by the elements mini script. Now we have a final transaction that lives inside Simplex. So, and as you can see, that's basically it. So 100 lines of code instead of, 300 lines of code overall. So here we get the lending parameters. We construct a final transaction, and then we have a very convenient interface to build it. So there's a function called add program input that accepts our program, and it also accepts a witness to spend this program. Then basically we are constructing this transaction in a correct schema, which our lending covenant expects. Just adding some program inputs, adding some inputs, basically implementing our business logic. And adding outputs that are also must be present to spend our lending covenant. And then we are just returning this final transaction upwards. So this function, the repay loan, is also used in the CLI, but now CLI is also much more simple. So as you can see, repay now only accepts one parameter, the TXID. Everything else is handled internally because we now have a convenient way to interacting with the Explorer. We can fetch everything. We can filter TXOs and all that kind of stuff. So we don't need the nasty parameters that we had before. So let's find this function. Okay. Here we are fetching our transaction, the lending creation transaction. We are extracting some parameters, which is basically a business logic because we encode some parameters inside UTXOs. So there is no, the other way of doing it rather than explicitly. Then we have a signer here that basically encapsulates and abstracts everything in terms of its UTXOs. We receive the UTXOs of our signer, and then we just need to create our final transaction. Actually, this call probably can be simplified, but it's even in that form, it looks much more trickier than before. So we need to provide this information to our repay loan function that constructs our final transaction. And what we need to do next is just call one function on signer and then broadcast the transaction. So the beauty here is that this finalize function is super powerful. As you can see, we didn't do any pruning, we didn't do any witness calculation, we didn't do any signing of UTXOs, and we didn't do any signing of seek hash all. We didn't provide anything here. So this finalize function figured everything out. It also figured out the correct fee to put into the UTXO and the correct change to return. Also, it implements a coin selection algorithm so that you really don't need to provide anything than the actual business logic inputs. So everything else is handled by this finalize function. And yeah, this is how our lending offer repayment looks like. So much better than it was before. Returning back to the wrong button. To the presentation. So boiler code was like 80%, and after Simplex, I estimate right now it is kind of 30%. So it's not perfect. We are at the alpha release right now. And yeah, the main idea is to reduce this boilerplate code even further to 10%, just allowing developers to concentrate on the business logic side of things. So yeah, here is what Simplex does under the hood. I will show the Simplex repository and we'll run some scripts after the slide. So yeah, Simplex does some management of contracts for you, and it can automatically generate like primitives for arguments and witness building. So it's not perfect, but yeah, simplifies things a bit. Then we have a nice SDK that has all the necessary functions, at least right now, for constructing and signing transactions. So also, it's not perfect. While we are iterating on this lending protocol, we are discovering that some pieces are missing. For example, we don't know how to work with state storage, and because usually state is encoded into taproot, so the address of the program changes when the state changes. Simplex doesn't understand this logic right now. So yeah, it needs to be updated basically. Probably there are like a bunch of things like that. So once we iterate to a more stable release, probably will cover more functionality. Yeah, then Simplex has integrated regtest that allows running reproducible tests. I'll show you exactly how it's done. It's yeah, super easy actually. Then we have a signer that is WeAware and supports confidential GXOs. So in our lending protocol, we didn't use this functionality because we wanted to make things as clear as possible. But Simplex does provide support for confidential UTXOs to preserve privacy. Yeah, and yeah, I estimate that now, for example, in the lending project, there's like 30% of boilerplate code rather than 80 than before Simplex. So yeah, let's take a look at the repository. So the repository structure is the following. We have Simplex app utility. Simplex app is a quick way to install Simplex. You can just run this command. It automatically figures out your architecture. We currently support Linux MD64 and Mac M1. If other platforms architectures are needed, just shoot an issue and we'll add support for them. So this command, it downloads an installer, and Simplex app downloads the rest of the Simplex. So the rest of the Simplex is those three binaries, which are archived. And basically, it's the CLI of the Simplex and elements D and the lectures that is used as a local regtest. So this command, basically it fetches the releases from our GitHub releases and downloads and installs everything to your machine, like changes the path so that you can call everything directly. Then the second thing that needs to be done is Simplex is a kind of two tools in one. So the first one is the CLI that gets installed by Simplex app, and the second one is the kind of library, the STD, so-called STD. The STD is just a basic cargo crate, and you need to add it to your cargo project to use the SDK signer transaction and test and basically everything else. But theoretically, you can use the SDK without the CLI for just, I don't know, if you need to use a provider or if you need to use a signer, like it's an isolated thing, you can install it separately. And then there is a usage file. So here is the current configuration that we have. Basically, those words indicate the actual commands that Simplex has. The build command, regtest command, test command. Here is the full list. Build, regtest, test. These are like three main ones that you'll be interacting with when using Simplex. And build command, it basically scans your project, and whatever you wrote here, it tries to understand in terms of simplicity, source code, filters out everything, and generates kind of Rust wrappers with concrete types, for example, for witness and for arguments that can be used down the line, and not worrying that you mistyped something. And then we have a regtest with a default signer, so you can pass any mnemonic. So yeah, it basically creates a signer from this mnemonic and sends the initial this amount of initial tokens to it. The test one is kind of the same. Also, you can connect to Explorer, or you can connect to a regtest by providing this configuration. Here's some explanation of every variable. Yeah, and also there is an example project, and I will actually show this example project right now. Boom. So the example project is the following. It is basic Simplex project. So we have a super basic covenant here. We call it pay to public key. It let me just move it somewhere. Okay. It just has a main function, and then in order to spend it, you need to provide a signature of Zcash, where the public key, kind of the owner of this script, is provided at the compile time. So let's see what we can do with this thing. So let me just delete this artifacts here, and I'll write simplex build. So simplex build generated artifacts for me. Let's just pick at what these are. Here is an artifact. You can see that we have source code exported here. We have some functions to construct our program, and basically this artifact is a abstraction over our simplicity program. Also, there is a fancy macros here, which generates a lot of witness and arguments code, but let's not go into that detail. Then let's see how the tests are written. So what you need to do is just create a tests directory, create some file there, and write this macro here. This will signal to Simplex that this is a Simplex test and it needs to be run. By that, Simplex understands that you expect some context, and context has some functions for your convenience. So let's just take a look at what those functions are. So two main ones is the get default signer and get default provider. So once you run the test, Simplex automatically creates the signer for you, a provider for you, where, for example, if you run the test directly without an external connection, it automatically spins up this regtest, creates a signer, and populates everything into the context. So if it is a connection to some external Explorer, then this provider will be connected to the Explorer. If it's a regtest that you created and are running in a separate terminal, all the endpoints to it, you can populate a config here with those endpoints, and then the signer would point to your local regtest that you created. So so here is two functions. So first one, it creates our pay to public key program, and the second one spends our pay to public key program. So the first function looks like that. We just need to get a default signer, and we need to get a public basically the script of our pay to public key program. So here is how you do it, and we have the arguments that need to be passed, basically like a constructor argument sort of, to compile our pay to public key program. These arguments, as you can see, are imported from artifacts, so Simplex generates them. and you can see that we need to pass a public key variable here. So it means that this struct is typed, and if you provide something to this struct, it will basically match whatever the covenant expects. So no way to mess up any types or encodings here. Then we are constructing our program. So because it is, so simplicity lives inside a taproot, we need to provide a taproot spending key. So in our case, we can't spend the taproot directly. We can only spend it through the through the script, through our simplicity program. That's why I'm passing the unspendable key here. And also I need to pass arguments, which basically constructs the program for me. Then I need to get the script. So here is how you do it. Just one function, basically. It returns the script. And then inside this function, inside the signer, there is a convenient send function, which basically sends the policy asset, the liquid BTC in our case, in that amount to the script you provide. Yeah, inside this function is pretty complicated, but to the end user, it is super convenient to use. So we can quickly take a look at what this send does. So under the hood, it creates a transaction with one output with policy asset and this script that we provide. It calls finalize and then broadcast. And this is the same finalize that we are using in our lending protocol. And yeah, it quickly gets a bit complicated, but yeah, basically what this function tries to do, it tries to construct the best transaction to be able to create those outputs requested. So the best transaction is the one that is like optimized in terms of outputs, inputs. It needs to understand the fee. It needs to understand the blinding and unblinding of UTXOs. And also it needs to estimate everything properly. And yeah, just construct it in the best possible way. So I will just quickly scroll through the code here. I won't go into the much detail. But yeah, basically we are trying to estimate the transaction with the greedy coin selection algorithm. And if the estimation is successful, we just return. The estimation is failed, then we want to add more UTXOs to cover the costs. So this estimate TX is also not a simple function to follow, but yeah, it tries to figure out whether we need any change or not. And yeah, just that does everything for the end user. And then we have this sign TX here that does all the pruning of our programs, or if no programs are passed, we will just assign the UTXO with the this SegWit version 0 signature convenience. So in the end, we construct our transaction, we broadcast it, and create the page public key program. The spending of the program is a bit more involved, but yeah, still pretty simple to follow, at least in the user side of things. So taking signer provider here, getting the program, getting the script of the program, and then I want to find the UTXO that I want to spend. So inside the provider, there's a convenient function which returns the list of UTXOs from with this script. Then I filter out any UTXOs that are not policy assets. Maybe someone sent some other asset to the same program. I don't want that. I want to leave only the LBDC. And then I need to construct a transaction that will spend this program. So because our pay to public key script expects a signature, so we somehow need to ask the signer to create the signature for us and put the signature somewhere in the witness. So because our example is kind of redundant because it doesn't have any other input, we just need to create a redundant witness here. So signature can be any value here. Yep. Okay. And then we are adding an input that we want to spend. So basically this UTXO that we fetched, and adding a program input with our program that we are spending and the witness of this program. And this line indicates to the signer that the signature needs to be provided to this field inside the witness. And then calling broadcast, and signer understands everything that we requested it. As you can tell, there is no output that I'm providing here because signer is kind of clever to understand that if excessive assets present inside this program, it needs to create a change that will be returned to itself. So this is not a part of a business logic, so users don't need to think about it, and they can just provide their code, and signer will figure out what to do with the rest of the tokens. That's why only one input is present here, no outputs. And yeah, then we broadcast the transaction, and if it's not a local regtest, we also need to wait for the transaction to be mined and included into the block. If it's a local regtest, then actually every transaction when you send it, it automatically gets included into a block, and the block gets mined. So the local regtest convenience is that there is only one transaction per block, and it's always the case. So let's see how to run this test then. Basically, what I need to type is simplex test. It compiles the example. It runs the basic test. Here it spins up the electors and elements nodes. So in the current release, it's kind of slow, but we have figured out how to speed up this process 3 times. So in the next release, it will be much faster. And also there's a second test, the confidential test that I haven't shown you. It is this one. Yeah, it just showcases some other features that can be used. For example, the create signer function. You can pass your custom mnemonic here. I will probably add a function to create a random signer if you need some just random accounts to test some stuff in the flow. And this code, it creates a blinded output. So from the user side of things, the only difference is this with blinding key call, and this indicates that the output needs to be blinded. So by passing this final transaction to Alice, this broadcast function understand that this output needs to be blinded, and yeah, just blinds everything.
Artem, in the Rust code there, I see that you're printing output indicating what the test is doing, like that broadcast on line 22. But I don't see that output appear in the Simplex test output.
This is the default behavior of the program, but you can type -- no capture, and then it will output in real time all the logs that may be present in the test. Yeah, sometimes you may not want to clutter, your terminal or the CI, or yeah, because the outputs or in this debug stuff may be pretty verbose. Yeah, so back to the confidential thing. Just one line of code indicates that the output needs to be blinded, and we send funds from Alice to Bob. And here on the line 27, we spend funds like Bob spends this UTXO. And this signer doesn't have any funds beforehand, so the only funds they have is from this one. And this means that the send function, it automatically understands all the unblinding, confidential shenanigans, and just works. Yeah, like that. So this is the basic example. I will then show the actual tests of our landing pretty quickly, because I'm a bit over the time. And yeah, let me find it. So contracts, tests, a bunch of tests here. Let's see the landing. Okay, just an export. So the repay, here we can see a Simplex test. And here is the repayment flow. Yeah, I believe there are a bunch of utility functions, but it all boils down to creating, sending transactions, and yeah, just some assertions that that are expected to not fail. Yeah, just quickly returning back to the presentation, so some future plans. Yeah, the main objective is to reduce the boilerplate codes down to 10%, to have even more user-friendly abstractions, but not to complicate stuff a lot, and to figure out the actual functions that developers need. I believe there are a bunch of functions that are still missing in the SDK. Then the big one is browser compatibility, both in terms of functionality and user flows. So we need to figure out how to properly compile Rust to WebAssembly with all the TypeScript bindings and all that kind of stuff to run Simplex in browser environment, and also understand how to interact with an external wallet. So of course, Simplex has its own signer, which expects a mnemonic to be present. We won't have such stuff in the browser. There will be some external wallet, either a browser extension or a mobile wallet. We need to figure out how to interact with it and request this wallet to do signing and transaction construction for us. There are some ideas how to do it, but they are kind of early to share anything here for now. Yeah, the integration with all the wallet API is basically this user flow stuff. Yeah. Then the Simplicity language team is currently working on adding support of modules and use keywords like pub keywords and all that kind of stuff to export, import functions into the Simplicity programs. So once this feature is merged, we'll need to figure out the dependencies management mechanism for Simplex because, yeah, we just want to reuse code, not to write everything from scratch. There will probably be some kind of standard library with some utility functions. So it needs to be some kind of somewhat managed and installed, discovered with the Simplex. Yeah, then the compiler management, which is also a complex topic, which touches backwards compatibility. The Simplicity HL code currently doesn't have any indication of like breaking changes. Users may install one compiler, then the new feature arrives, new syntax arrives, and this version of compiler kind of doesn't work anymore. So we will need to implement some compiler version management into Simplex to download proper compilers, proper binaries, so that all the Simplicity programs are compiled properly of the certain project. And then the regtest speed up. So we found 3 times optimization already, but obviously it's not even close to what I want to achieve. But the other thing is cheat codes. The idea is to allow users to just cheat the elements and say, for example, that they want some random UTXO to just appear out of nowhere, or create some, tokens out of nowhere, just bypassing all the checks for testing conveniences. Yeah, this one is also kind of hard to achieve, but would be nice to have. So yeah, that's it. Here is once again the Simplex GitHub. Here is my X account if you want to get in touch. So if you have any questions or anything, yeah, just please ask.